Okay. So in this talk, I'll talk about dynamics of senescent cells, and in the next talk, Yifan Yang, who's a student of Uri Alon and now doing a postdoc together with me, will talk about continuing these ideas to talk about aging in bacteria and a potential universality between mammals and bacteria. So I'll talk about work done by Omer Karin, who's a fantastic PhD student from a computational background in collaboration with Valery Kryzhanovsky, Senescent Cell Lab at Weizmann, and Amit Agarwal, a PhD student. When we think about the hallmarks of aging, that's one way to understand aging, and these epidemiological curves that we saw in the previous talk is another. And we want to link, how can we link molecular damage to things like the Gompertz law? And it's striking that genetically identical animals die at different times, just about as different as non-genetically identical animals. So it's not the genes, it's not the environment. They're raised in the same cage here, these mice. And it's something else, something stochastic that determines the widening differences between aging individuals. Where the individuals become more and more different as we age in terms of health. And there are regularities, on the other hand, to aging, like the doubling of hazard in humans and mice and many other animals. Hazard of death in a given year goes up exponentially with age. By the way, this plateau here is mainly suicides and accidents. If you extrapolate extrinsic mortality down, it goes down exponentially all the way down to here. And I'm going to pretend in this talk that there's one causal factor for all the other causes of aging. Of course, this is not true, but let's pretend that it is, just to make progress. And I'll talk about something that, a factor, senescent cells, that is pretty exciting biologically. These are cells that become damaged and stop dividing, and they have very important roles in wound healing. So they probably evolved so that when you have damage, cells don't commit apoptosis, you don't get a hole. They just become senescent, and then they call in the immune system to remove them. So they're important for wound healing, and they indeed secrete inflammation factors and also factors that slow down regeneration to help healing. But we weren't designed to be old. And as we get old, the amount of senescent cells in the body, in mice, in humans, etc., grows up almost exponentially with age. So senescent cells accumulate, and then it's as if we have wounds all over. They make chronic low-grade inflammaging. They reduce stem cell regeneration, and this causes many diseases. These are causal factors for many diseases, and the field was rocked in 2016 when removing senescent cells starting in middle age turned these mice. This is two genetically identical mice. This is a 2-year-old mouse. This is a sibling, senescent cell removed once every 2 weeks since middle age. And since then, many papers showed that almost all diseases, age-related diseases that have been studied, are ameliorated by removing senescent cells. So senescent cells are at a sweet spot. They can be formed by many kinds of damage that we've heard about in this conference: mitochondrial damage, protein damage, etc. can cause senescence, proteostatic damage, and they cause something very physiological: chronic inflammation, stem cell exhaustion. So if we can understand senescence, maybe it's a sweet spot for understanding how these different damages lead to a physiological response. And these are a list of diseases where removing senescent cells helps. So in our research, we were asking, how do senescent cells accumulate? Do they just passively accumulate, or are they removed and made and removed quickly? And something changes about this removal and accumulation process. What is the half-life of senescent cells? To address that, we began with data from Bird et al., which had a luciferase assay for P16. So many of these cells, senescent cells, now emit light to first approximation. These are 33 different mice. See, senescent cell or luminescence goes up with age. This goes up until late middle age because of some technical problems. And we got from them the data, the longitudinal data. So each mouse, we could tell how many P16 positive cells, like senescent cells, there are. And you see, senescent cells go up and down more than the experimental noise. So we have this kind of notion of production and removal. And so here, as systems biologists, we wrote a production and removal. So production minus removal plus noise, a stochastic equation like this. And in fact, since we don't know, we explored the space of unknown. We took the basic interactions that could be, like production of senescent cells can increase with age. Senescent cells make other cells around them senescent. That's like an autocatalysis. the removal can decrease with age, and senescent cells can inhibit their own removal. That is to say, the immune system might decline with age, but senescent cells might grow so much that they saturate the immune system and inhibit their own removal. By the way, they're removed by macrophages and NK cells. If you mutate NK cells, mice become full of senescent cells and die and have progeria, etc. And I just want to recommend this review by the Kirkwood group on the evolution of cellular senescence that talks about these processes and is also very interesting, thought-provoking. So we have 16 circuits, because you have 4 possible effects, could be there or not, 16 possible circuits. And we used max likelihood to explain all those 33 mouse trajectories. And it was quite clear that the best models have the following features. They have production that increases with age, so production rate increases with age, and removal saturates, like a Michaelis-Menten enzyme. So senescent cells slow their own removal. It's not necessarily to have removal decline per se, but senescent cells should slow their own removal. And why does senescent cell production rise with age? My favorite explanation is that, I mean, what's the difference between us at age 10 to 20 and 70 to 80? Something is different, and that's it can't be just cells that are replaced like skin cells, because they only last a month. It has to be something that stays in our body. So my favorite hypothesis is that you have stem cells, they divide about a constant rate when you're an adult, and supposedly become mutant in a way that doesn't harm the stem cell, but the differentiated cell expresses now mutant protein. Maybe they're unfolded, get carbonylated or whatever, and that becomes damaged and therefore senescence. And so with age, we have here, let's say, a mutant stem cell in a column of senescent cells. Then here, then here, then here, then here, then here. And our body becomes full of these senescent cells. And that's why we have this rising production rate with time. And age-related interventions in this picture, like the molecules we heard in the previous talk, or evolution of longevity in different mammals, maybe increase repair and slow down this process, and therefore slow down the rate of accumulation of senescent cells. And this EDA is actually what determines longevity in this model, this slope of senescent cell production rate, and is an important parameter. So this model works wonderfully on the average and standard deviation and distributions of the senescent cells, and also explains something very important, that as we age, senescent cells can fluctuate. When we're young, they fluctuate a lot. When we're old, they fluctuate slowly. So if you're above average, you stay that way longer. And if you're below average, you stay that way longer. This is the chance part of aging. If you're unlucky enough to be above the average, you stay that way longer because senescent cells inhibit their own production. And that is captured by this model and by the data. So persistence with age. Why is there widening differences with age? And the model also predicts senescent cells have a half-life of days in the young and weeks in the old. And we set out to test that by direct experiments on mice. We added senescent cells by giving a drug in the lung. After 5 days, it's full of senescent cells. And then we measured senescence at different time points to see what happens. And we measured senescent cells by kind of state-of-the-art assay of beta-galactosidase and imaging FACS. And we found that in young mice, senescent cells are turned over every 5 days. So there's a balance of removal and production. And in old mice, they're turned over once every month or so. And that's right on what we got from this luciferase data from the mice. So we got a pretty good confidence that we have some understanding that senescent cells are produced more with age and they slow their own removal. The removal gets slowed down, and so they have a longer half-life. Now let's go back to the question asked. Does this process, can that explain things like the Gompertz law, exponential growth rates? So to do that, we have to understand how senescent cells link to death. And we don't know how to do that right now. But since they're linked to so many illnesses, let's make a simple assumption, going back to the 50s, that senescent cells, in each individual, they fluctuate, but when they cross a certain threshold, let's say, that's incompatible with life. So this becomes a first passage time problem. We have a model for the stochastic senescent cells, and we can ask, when does it cross a threshold? And the amazing thing is this particular equation that I showed you has the property that crossing a threshold, it gives you this exponential hazard. So it has the Gompertz law in it. And you can even get the Gompertz slope. It's this rate of damage production, the threshold divided by the noise. By the way, this is the intrinsic mortality we heard in the previous talk, all the suicides and stuff. So if you add that, you get a pretty good understanding, and you can get parameters for humans. If you extend this model, of course, not all organisms have senescent cells, but a lot of organisms have the Gompertz law. If you try to extend it to invertebrates, but not thinking of senescent cells, but other kind of damage that's produced and removed and saturates its own removal, you can explain things like how shifts in life-extending diets make hazard curves shift within days to new curves. This data by Partridge Lab. Because of the fast turnover time of senescent cells, when you shift, the senescent cells just go away so quickly. And that's a kind of a indication that you have this fast process of turnover and a slow process of changes in the parameters. In this case, we think the production rate. And another wonderful result by Nick Strustrup is the scaling of C. elegans survival curves. If you have different life-extending perturbations and you plot age by the average age, the curves tend to fall almost exactly the same. And that's also explained by this model, but only when these perturbations affect the rate of damage accumulation, this eta, the change with age of damage accumulation. Any other parameter you get a different slope. So that goes back to the previous talk. If you get a different slope, that's a different parameter in the model being affected. If you get the same slope, just different longevity, it's this rate of damage accumulation according to this picture. So that's what I'm saying is there's a lot of experimental data that a simple model can capture, and it's unusual. Not many of the models can't do all of that, can't give you an exponential slope, etc. And finally, I want to talk about how this might relate to disease incidence. So if you look at different diseases and you ask incidence, that's like hazard. What's the probability of getting the disease at age 50? You know, out of all the people who haven't gotten it yet, who are still alive, at age 60. So for many age-related diseases, you see an exponential rise, yeah, and then a drop at very old ages. That's well known. You don't see that when you look at like prevalence or like the integral over this, but if you ask about hazard, you can see the drop at old ages. So how can we explain this? We basically use the same model. We say something like this. There's a physiological parameter, for instance, in cancer. There's how the immune system removes the cancer cells. So if cancer division is slower than cancer removal, the cancer can't grow. All these precancerous cells. Now imagine the senescent cells go up, and they start saturating the immune systems that removes them, right? At some point, there's so many of them. You're not designed to be old. So you have so many macrophages and NK cells. They have to do many things, like fight cancer, but now they're actually removing senescent cells. So the removal of cancer goes down. At a certain threshold level, cancer proliferation exceeds removal, and you get cancer. So there's a threshold lower than the death threshold. And if senescent cells cross that threshold, that's a simple model we made, you get the disease. But then the question is, why doesn't everybody get this disease? Because everybody's going to cross this threshold before the death threshold. So we also say only a fraction S of the population is susceptible to each disease. Some people are susceptible to diabetes, a different set of people susceptible to IPF, etc. So we model each disease by a threshold and susceptibility. And with that, you can get these incidence curves. The exponential slope is just given by the threshold, as I told you. It's like a slope is eta x critical divided by epsilon. So you get the slope from this first passage time problem. And the drop at old ages is because at old ages, everyone susceptible has already gotten the disease. So this heterogeneity accounts for the decline. And we tested that with a huge database we have for half of the Israeli population over 10 years, 50 million life years. We have 500 disease incidence curves, and you get these very nice fits. There are some exceptions, like for instance, osteoporosis in women after menopause is not captured. Something about menopause isn't captured by this model. Or dementia also appears to rise with a slope that's too high to explain. It's higher than the death threshold. So maybe in the brain there's something different. It's not senescent cells, it's a different kind of damage or senescent cells. So there are exceptions, but most diseases and cancers fit into this picture. And just to finally say that in the model, in silico, we can now ask what happens if you remove senescent cells, let's say with a drug like a senolytic or immunotherapy cell, CAR T cells that kill senescent cells, or maybe a diet that increases repair and therefore decreases the production of senescent cells. Any of these is predicted to, if you take an incidence of a disease, to within quite a short time reduce the incidence, and you can get a decade shift in incidence. Even if here you assume that only 25% of the senescent cells are susceptible to the drug, and you give it once every month. Why once every month? Because we think we know the half-life of senescent cells. You don't need to give it once every day. You need to give it once every month or 2 months so the senescent cells can reaccumulate, not too much, right? So you don't want to give these drugs too often because they have toxicity effects. So we can calculate kind of the optimal rate. But even if you kill just a little bit of the senescent cells or the damage-causing cells, you get a shift of decades in virtually all age-related diseases. And so you can expand health span. That's part of the Giro science hypothesis. And that'll be very interesting to observe once there's trials on drugs that, like metformin, that are thought to reduce senescent cells, and through the mTOR pathway maybe reduce production of senescent cells, etc. This is just speculation. So to summarize, senescent cells turn over rapidly in young mice and slow down, repair slows down in old mice, and the stochastic model shows a kind of critical slowing down phenomenon that gives you the widening between individuals, non-genetic individuality, widening between individuals, longer persistence with age, so that if you're worse off, you stay that way for a longer time, and the exponential rise of hazard and disease incidence and scaling of disease curves and fast, slow transitions with dietary response. So a lot of aging phenomena in this kind of family of stochastic models. And there's more things I can say, but I'll stop here. I noticed that I was talking for 20 minutes or 19 minutes, so great.
I mean, Uri, if there's more that you would like to say, you do have a few more minutes. That's plenty of time.
Maybe I just wanted to say that there's these parabiosis experiments where you connect the circulation of old and young mice, and the old mice become a little bit younger, and the young mice become slightly older. And that can be explained by the same model, where the young mice have spare capacity of removal, have these extra macrophages and NK cells, and they flow to the old mice, and they can help their saturated removal. So we're thinking, just as a metaphor, that the young mouse is like a small village making garbage, the garbage senescent cells, and it has 100 garbage trucks. That's the macrophages and NK cells, which is fine to remove the damage. When you're old, you're a big city and make a lot of garbage, but you still have those 100 trucks. So they're saturated and this garbage piles up. But when you connect two mice, you make an alliance between a village and a city, and some of those trucks from the village can go to the city and improve things greatly in the city at slight expense to the village. And that picture explains a lot of data, including the reduction in senescent cells recently measured in parabiosis. Okay, so maybe I'll be very happy to see if there's any questions and learn something from you, from the audience. And of course, this is like many other reasons for aging. If you delete senescent cells, organisms will still die, but maybe about this way of thinking.